ETS 551, Digital Signal Processing. Chapter 1. Introduction to Digital Signal Processing. Definition of signal and system. Definition of signals: any physical quantity, voltage, current or velocity, that varies with time, t, or independent variables and carries information. For example, below. Signals may be classified into two categories depending on the characteristics of the time variable they can take: continuous time signal, discrete time signal. Classification of discrete time system. A discrete time system is a system that operates on a sequence of discrete time inputs, a discrete time signal, and produces a sequence of discrete time outputs. Breaking it into two main ideas, which are system stability and recursiveness, here's a simplified way to explain it. Stability: stable versus unstable systems, left side. A system is said to be bounded input bounded output, BIBO, stable if every bounded input produces a bounded, finite, output. A system is said to be stable if a bounded input to the system will produce a bounded output, BIBO. An unstable system usually exhibits extreme behavior and causes overflow in any practical implementation. Recursive versus non-recursive systems, right side. A system whose output y, n, at time n depends on any number of past output values. Example, y, n1, y, n2, and so on, is called a recursive system. Example, y, k equals y, k minus 1, plus x, k. In contrast, if y, n, at time n depends only on the present and past input, then such a system is called non-recursive. Example, y, k equals x, k, plus x, k minus 1. Stability of discrete time system. What is BIBO stability? Definition: a system is BIBO stable if for every bounded input x, k, the output y, k, is also bounded for all values of k. Think of it like this: if the input doesn't blow up, neither should the output. Mathematical condition: the system is BIBO stable if the sum of the absolute values of the impulse response g, k, is finite. The system is BIBO stable if the sum from k equals 0 to infinity of the absolute value of g of k is less than infinity. This means the system's response to an impulse must die out over time, not grow forever. For systems with distinct real poles, the system function in the z-domain is given as a sum of partial fractions. G of z is equal to a1 times z over z minus alpha 1, plus a2 times z over z minus alpha 2, and so on, until an times z over z minus alpha n. The inverse of this, in the time domain, gives the impulse response. G of k is equal to a1 times alpha 1 to the power of k, plus a2 times alpha 2 to the power of k, and so on, up to an times alpha n to the power of k, all multiplied by mu of k. Here, mu, k, is the unit step function. It ensures the response starts from k equals 0. Alpha sub I are the poles of the system. Key stability condition: the system is BIBO stable if all poles alpha sun I satisfy. The absolute value of each pole alpha sub I must be less than 1, this means the poles must lie inside the unit circle in the z-plane. Bottom graphs. These plots visualize different impulse responses. Some decay over time, stable. Some grow or oscillate uncontrollably, unstable. The arrows and X marks at the bottom indicate pole locations on the real axis, helping to visually determine whether the system is stable, inside the unit circle, or not. Next are stable versus unstable systems. In theory, in discrete time systems, we look at how the system reacts to an impulse, a sudden input, as time goes on and on. Based on this reaction, we decide if the system is. If the magnitude of h, n, tends to infinity as n tends to infinity, the system is unstable. This means that at least one pole of the system is outside the unit circle, or poles of multiplicity greater than 1 are on the unit circle. At least one pole has a magnitude larger than 1, or poles of multiplicity greater than 1 have a magnitude of 1. The magnitude of z equals the magnitude of e to the power of a times t is greater than 1. If h, n, tends to 0 as n tends to infinity, the system is stable. This means that all poles of the system are inside the unit circle. All poles have a magnitude less than 1. The magnitude of z equals the magnitude of e to the power of a times t is less than 1. If the magnitude of h, n, remains bounded by a constant m as n approaches infinity, the system is marginally stable. This means that there are some poles on the unit circle with no more than a multiplicity of 1, and the other poles are inside the unit circle. The magnitude of z equals the magnitude of e to the power of a times t is equal to 1. This is for a complex pole pair. The system is BIBO, bounded input bounded output, stable if the magnitude of the pole, which is r, is less than 1. For the graphical interpretation, the unit circle in the complex z-plane helps determine stability, poles inside the circle, stable poles on the circle, marginally stable poles outside the circle, unstable. The three diagrams on the right show how the output signal behaves for different pole locations. Marginally stable, oscillations continue with constant amplitude. Stable, oscillations die out over time. Unstable, oscillations grow over time. Figure 1 shows the unit circle with the regions of asymptotic stability. Note that the sampling rate, t, can affect the transient response of a system, such as the type and stability. The settling time for a system is found by examining each of the poles, similar to continuous time analysis. The estimated 2% settling time is t, is equal to -4t over the natural log of the magnitude of the pole, where t is the sampling period. The overall system settling time is the one that takes the longest to die off. The dominant pole for a system is the pole that yields the overall settling time for the system. The dominant pole will be the one that is furthest away from the origin, while also considering that the system must still be stable. Unlike analog control systems, in digital control system sampling rate affects the transient response as well as stability. Thank you and see you on the next video.